All right, happy Friday, everybody. As you know, we have limited time, so you should hopefully be already in your seat and starting on your do now. You're going to have 3 more minutes to go ahead and work on this, and we're going to quickly go over it. Again, 3 more minutes, silent and solo. You can pause the video here. All right, so coming back to this, in our lovely do now here, we have that Sam went on a road trip that took several hours on a single highway, and there was no traffic. To pass time, he paid attention to the mile markers. He got on the highway at mile marker 135. He kept track of the time that passed and what mile markers he passed. Sam decided to plot the points he collected. Below is a table and a graph Sam created based on his data. All right, so we have a number of hours traveled here. We have our lovely different mile markers. And then we have this graphed out very nicely for us. So A says, in Sam's road trip, what are the 2 quantities involved? Well, the 2 quantities involved are simply the 2 variables that we have. So we have hours or time. Either one would work. Hours traveled or time. And then we have mile markers. And then for B, it's asking us true or false, the number of hours traveled depends on the number of mile markers passed. Let's take a look at that, right? Because it's really saying, is our time our dependent variable and our mile markers our independent variable? And if we look at both the graph here and this table, we can hopefully see that that's actually not going to be the case. Right, because remember that this vertical axis is normally going to be our y-axis. In this case, it's the m-axis, but this is always our independent. Or sorry, this is always our dependent. Apologies. So this is always dependent up here. And this one here would normally be our x-axis, or in this case, our t-axis. This is always our independent variable that we place running horizontally. And so that means that our hours traveled should be our independent and our mile markers should be our dependent, which is the opposite of what this is saying. So I know that this is going to be false. That is not true. And so looking at C now, it's again a true or false statement. This time it says the number of mile markers passed depends on the number of hours traveled. And that makes sense, right? We're going to circle true because that's what we just said. We know that hours traveled is our independent variable and that the miles markers passed are dependent because this is what relies on how long we've been traveling, right? Which makes sense because if he's not traveling at all, then he's not going to be passing mile markers. So therefore, these numbers here are going to be dependent on these here. So then D says, based on how you answered in part B and C, what is the input and output on Sam's road trip? Now, input and output are something that we've talked about before. We're going to kind of formally define them today. But remember that input is really another way of saying our dependent variable. And so this is going to be our hours traveled, which means that our output is going to be our mile markers passed. So again, our input is their hours traveled, and our output are the mile markers passed. Take a quick 30 seconds, make sure you have this down, and then take another quick 30 seconds and make sure you have your notebooks on your desk and open to a new page. You can go ahead and pause the video here. All right, so on that new page, make sure your date's at the top. Now there's a lot going on here, but the first thing we actually have to do is we have to come all the way down here, and we need to finally kind of formally define some things that we've seen before and that we've definitely talked about, but never fully written down. And the first one here is function. Now, formally, we're going to state that a function is a relationship in which each input has exactly one output. And this exactly is very important here. So again, a function is a relationship in which each input has exactly one output. Well, if we know that that's what makes a function, let's talk about what makes an input and what makes an output. And we sort of just kind of briefly talked about it on our do now. But our input is the independent variable for a function, and the output is the dependent variable for a function. We can call this x, we can call this y. So names we've seen before, we've seen x, we've seen t. Up above it was just h. And our output, we've seen y, we've seen h, we've seen m, we've seen c, we've seen a lot of these, right? And so take 10 seconds if you need to, go ahead, pause the video, make sure you have these down, because then we're going to put these into some context. Okay, so today we're going to actually be looking at what makes a function. How do we define a function? And one of the easiest things to really see is what doesn't make something a function, right? Because function has clearly a set of rules, as we just established a little bit before, where it's a relationship in which each input has exactly one output. So in order to see if something is actually going to be a function, like in example 1, we need to see if it actually violates those rules. So what we're going to do is we're going to look at each input, right? Each x value here. I have 3, -4, 5, and 6. Now those are all unique numbers. There's no repeats. And so I know that each input has its own output. So I know that this is in fact going to be a function. And really what I'm looking for here is there an x value that gets repeated that has two different y values? For example, you can see here that I have a 2 and a 2, right? So 2 as an output gets repeated. But it's okay when we're looking at this for outputs to be repeated. That's all right. We need to make sure that our inputs or our x values or our dependent variables are not getting repeated. So if instead here, if I had, like everything the same, this 3, 2, -4, 1, 5, 2, and then on the end here, instead of having 6, 4, I then had 3, 4. Well, then I would say, hang on a second. I have 3, 2, and I have 3, 4. This input of 3 no longer has exactly one output, right? Because it now has 2. It has 2 and 4. And this violates the very definition of a function. So if we were looking at a set of points that looks like this instead, we would say, well, no. This is now not a function because it violates that rule. And so looking at B says is the following relation a function. And so as you can see, the lovely essential question here is going to be, does every input have only one output? And when we're looking at something graphically, we actually have a neat little tool that we'll use, and that's called, and make sure we write this down, this is the vertical line test. You may see it abbreviated as VLT, but this is the vertical line test. Now the vertical line test is a very simple check that we use when looking at something graphically and trying to determine if it's a function. What this means, or what this test is if we take this and we were to draw a vertical line anywhere on this, in order for this to truly be a function, it should only be hitting this vertical line once. because this vertical line represents an input, right? In this case, it's sort of right on -3, a little bit to the left of it. But this is representing the entirety of -3 as an input. And as we talked about, that input should only have one output. But if we're looking at this, we see, hey, this crosses twice, which means that -3 here is actually going to have two outputs. And I know what they're going to be, right? They're going to be here and here. It's going to be about 3 and about -3. So because this one input has two outputs, or it crosses that vertical line in more than one spot, I know this isn't a function. This is not a function, and it doesn't pass our vertical line test. All right, take 30 seconds, have this down. In your notes, I want to see this set of numbers written out, and I want to see just a quick sketch of this graph. It doesn't have to be anything crazy. Just go ahead and make sure that you have some sort of either oval or circle graphed so that you can show if we use our vertical line test, it's going to hit in multiple spots. Go ahead and pause the video here, and once everyone has this, we will be back together. All right, so now we're going to take a look here, and we have function notation. And we've seen this before. We've actually sort of talked about it. I know some people have had some questions on it. But function notation is what we see here. This is function notation. So instead of seeing y equals, or h equals, or t equals, or any other letter, we're actually saying f of x equals 3x plus 5. And so we've seen this before, specifically with g of x and h of x. We've seen it there, but it's important to note that this is saying the same thing as though we had a y or a t or any other singular letter. This f of x is just being a little bit more descriptive. And so copy this line here down into your notebooks, and we're going to kind of pick this apart, and we're going to just make sure that we can label each part of this, right? Because after we get this down, I know that if I'm looking at this f of x right here, this, just as though it were a y, is still going to be my output. That's still my output. And this x, well, this x hasn't changed, actually something we're still really familiar with, and I know that this is my input. And so it's important to note too, there's not an arrow drawn to it yet, but I'm going to draw my own here, that this, what goes inside the parentheses, that's also your input. And so function notation lets us just be a little bit more specific. We're saying, hey, we have this output f of x, but really we have this function of x, because x is our input. Now, if we had another letter over here, and say we had like n, so if this was equal to instead 3n plus 5, function notation is going to dictate that this is going to be f, or any other letter for that matter, but it's going to be f of n, right? We would no longer have f of x equals 3n plus 5, because then, well, we don't know what this n is. We don't know, we have no input. And so it's important to know that whatever goes inside the parentheses right here, this is always our input and should always match what's on the other side, whether it be a letter or even a number, which we'll talk about in a second. And so when we're looking at the coordinate point, what we've seen before right here is our lovely x comma y. In this case, using function notation, it's going to look very similar, but we're going to have x, and instead of y, we will simply put f of x, because again, that's our output. And so let's take a look in terms of kind of what this looks like, and can we turn equations that we are used to seeing into function notation? The answer is yes. It's actually easier than we would expect. So example 2 says that if Sam's distance can be modeled by the function m equal to 58h plus 135, rewrite this equation in function notation. Now in your notebook, I want you to make sure that you have this equation down. You don't have to write this entire thing, but make sure you have this equation down. And if I'm going to rewrite this, well, I know that my output is right here, and that's my lovely m, and I have an input h. And so I'm going to model exactly what's over here. I'm going to have that m of h is equal to 58h plus 135, right? We're not changing the actual structure of the equation itself. We're simply just rewriting how we actually write our variables, again, so that we're more specific. And the reason we do this is then, because in example 3, we have evaluate m1 and explain the meaning in the context of Sam's scenario. So when we have something that looks like this, m of 1, remember, this still holds true. M is still definitely, or well, this entire phrase here is definitely still the placeholder for my output, but instead of x or h being my input is going to be 1. And so this is actually a super specific way of saying, hey, you're going to evaluate this equation at 1. And so m of 1 is simply going to be equal to 58 times 1 plus 135, which is going to be 58, because 58 times 1 is still 58, plus 135. And so I know that m of 1 is equal to 193. So again, this is going to be our input. Remember that our input has to match on both sides. And then from there, we simply just calculate this out. All right. Take 30 seconds. Make sure you have this down. Again, make sure you have this equation with its parts labeled. Make sure you have how we rewrite a coordinate point. I want to see m equals 58h plus 135, and whether you have arrows then drawn or however it is going to be able to tell you to know that, hey, rewriting this in function notation is this here. That works. And make sure we have these clearly defined as well. All right. Go ahead and pause the video if you need, but then when everybody has this, we're going to move on to problem set A. All right. So problem set A is 6 questions. It's 6 questions, and each one is very simply just asking you, is this a function or is it not? If it's not a function, it's important that we read our directions here. We need to provide at least one piece of evidence stating how we know it's not a function. So we need to provide at least one piece of evidence stating how you know it's not a function. If it is a function, you don't need to state your evidence. It's only when it's not a function that we need to state our evidence. So go ahead and work on this silent and solo. For these 6 problems, you're going to have 5 minutes. 5 minutes silent and solo. Problems today 1 through 6. Go ahead and begin. You can pause the video here. All right. So hopefully you were able to get through those. Hopefully we're starting to kind of be able to see what makes a function, what doesn't make a function. But I'm going to pick some key ones here that we're going to kind of go through. First one is going to be number 1. So number 1, again, I'm given a list of points. I have 6, -1, -2, -3, 1, 8, and -2, 5. I'm going to do the same thing that we did in our notes, where we looked at our inputs. I'm going to see that all of these are unique numbers. None of them are repeated, which I take back, because if you notice, we have 2 -2s, right? So these, in fact, are not unique. And so if these aren't unique, that means that -2 has 2 outputs, right? It means that it has the output of 5 and -3. But given the rules of what a function is, each input has to have exactly one output. So I know that this is not a function. And for my evidence, well, that's why. Because -2 gets repeated and has two different values. Now, it's important to note, if this 5 were instead a -3, and they had actually just rewritten this point, it would still be a function, because it's actually just listing that same point twice, right? It's saying, hey, -2 still has the same output of -3. But because these are different, that's what's going to cause concern, and therefore have this not be a function. Jumping down to number 3, we're going to do the same thing, right? We're going to look, and this time I do truly have all unique numbers. I have 5, 10, 15, and 20 as my inputs. And so I know that this is in fact going to be a function because each input has exactly one output. And if you had looked at this and gone, well, wait a second, we have 20 showing up twice, and we have 30 showing up twice. Remember that that's okay, right? Because these numbers here, these are our outputs, and we're not actually looking to see that our outputs are unique. It's only our inputs. And so if you want to a way to visualize that, a horizontal line is still a function. It's still a function. It passes that vertical line test. Each input has only one output. It just happens to be that in a horizontal line, all of the outputs are the same. And again, that's okay, because what we're looking for is to see that our x values, or our inputs, or our independent variables are not repeated as they were in number 1. So then we're going to look at number 4. Number 4, we're given 2 sets of values for x and for y, and some arrows indicating exactly what they are. Now, I would say if you're looking at this and there's kind of a lot going on, to make this easier for you, write out a list of what this is actually saying. So first I have -1, 9. Okay, so I have the point -1, 9. I then have -2, 8. -3, 7. And then -4, 8. Again, I'm looking at this column here and seeing that none of these get repeated, and they don't. And so I know, hey, just like before, this is, in fact, a function. Check. And lastly, I want to look at number 5. Now, number 5 doesn't have a whole lot of numbers. The graph is clear and evident, but the scale is really small. It's difficult to see. So this is where that vertical line test is going to come in handy, right? Remember, that's the vertical line test, or our VLT. And what that says is that we want to take a vertical line, and you can draw it anywhere at all you want on this graph. I wouldn't draw it over here, because obviously you want to see where it's coming in contact with your actual line. But I'm going to go ahead and draw mine right about here. Not quite a vertical line, I know. But looking at this, I know, hey, it crosses here, but it also crosses here. And remember that for the vertical line test, we only want one cross for this to be a function. Anything more than that, and it is not a function. We see that, hey, I have 1, and I have 2. Therefore, this is not a function. As far as our reasoning, it's because it does not pass the vertical line test. All right, and if you have any burning questions, I can say really quick that 2 and 6, they are in fact both functions. 2 and 6 are in fact both functions. Make sure you have the ones that I went over down and correct, and make sure you have that reasoning for each of these that are not functions, because you do need them. Go ahead and pause the video if you need. Otherwise, we're going to keep on moving. We're going to go to problem set B. Specifically, I want you to do problem 1 of problem set B. You're going to do problem 1 of problem set B. Silent and solo. Take about another 5 minutes. It does have 4 parts. Take 5 minutes, silent and solo, begin. You can pause the video here. All right, and bringing it back together, we're going to try and go through this kind of quick. We know that Jacqueline is riding her bike in a marathon this weekend. Her speed in feet per minute can be modeled by the function f of t is equal to 3t squared plus 5t, where t represents time in minutes. Convert each of the following statements to function notation, or convert them from function notation to context. So if I have f of 1 is equal to 8, what this is really saying is that after 1 minute, she is traveling, let's say moving, at 8 feet per second. And then B, it says that Jacqueline's speed after 2 minutes is 32 feet per second. Well, we're actually going to go the other way. What this is really saying is that, hey, f of 2, this function value where 2 is our input, is going to be equal to 32. And C is almost identical, just going to be different numbers. So we're going to have that f of 3 is equal to 42. All right, make sure you have these down, and then go ahead and jump to your exit ticket. For your exit ticket, I'm really looking at you're getting something down for 1 and for 2. Again, 1 and 2. You have until the end of class, silent and solo. Go ahead and begin.